Calculus BC, we're looking at section 5.5. Our learning target, you can see at the top, I can evaluate integrals using U substitutions. And look at this opening statement. Sometimes an antiderivative cannot easily be found. In such cases, at least for now, we will use the method of substitution to evaluate such integrals. Now, what is really going to happen is we're reversing the chain rule. That's what U substitutions are generally about. And the chain rule involved one function being composed inside of another. Another function was substituted inside of another. And if you can even look at an integral, and if you can see one function that is inside of another, we're going to call that function U and then make some adjustments. So that's really the big picture. Let's take a look right now at example 1. I think right now, if anybody were to look at this, I think without a doubt, everyone would feel very uncomfortable and say, well, there's no algebra that I can do to change this up. There's no obvious antiderivative that I'm recognizing. So what's going to happen, this happens quite a bit, is you begin to say, hey, do we see one function inside of another? Well, certainly we have a square root function in this integral. What we can do is say, let's let U equal the 1 plus x squared. Let U equal the 1 plus x squared. And that's honestly where we're headed with this. Well, what do we do now? Well, we're going to take a derivative on both sides, but tell you what, rather than write du dx, I'm just going to say the derivative of u would be 1, but we'd write just du. Here, if I were to take the derivative of 1 plus x squared, let's just call it 2x and just write dx after it. Now, right here, you can think, well, why in the world are you doing that? Well, could we have done du dx equals just 2x? Could we have done that? Of course, but look, what ultimately is happening whenever we're taking the derivative on the right side here, we'll just have a dx. This will speed up the process. So the whole point is there is a dx over here. Here's the real reason why we're taking our derivative a little bit differently right now. See, I'd like to know what that dx really is. I'd like to solve for that. So I'm going to say dx is really du all over 2x if I solved for dx. So now I'm going to make some changes. I'm going to take my integral, and I'm going to say this problem is the integral of 2x. I've got the square root, but look, in green I had that 1 plus x squared. And what really was that 1 plus x squared? Well, I think we all know the 1 plus x squared was really the u, wasn't it? So I'm going to just write a u right in here. The dx, you can see right here, is du all over 2x. So look, your 2x's cancel out. Now look at this. This is fantastic. The square root is really u to the 1/2. Look, you've got a brand new problem, brand new integral, and it's much, much, much easier looking. Here I can just do a basic antiderivative like we even did in chapter 4. Look, bump your power up by 1. That becomes u to the 3/2. Dividing by 3/2 is the same thing as multiplying by 2/3. Don't forget the arbitrary constant. Now imagine if you were helping a friend on this, and if you said, oh, hey, I'm getting an answer of 2/3 u to the 3/2 plus c. Your friend very quickly would say, are you doing the same problem that I'm doing? My problem has x in it. Well, you know what? We're going to have to resubstitute back in to finish this off. We're going to say, you know what? Your final answer, u, is really 1 plus x squared. And this is all raised up to the 3/2 power plus c, and that's your final answer. The beauty of it, too, is if you're really nervous about this, you could take your derivative the answer you would get would be the integrand, what is inside of the integral, and you could walk away feeling pretty confident. So this is really the bare bones of what's happening with our U substitutions. Let's do another problem here. Let's look at number 2 and look for a function inside of another function, and that's going to be the key for a U substitution here. You look, you'd say, wow, I've got cosine of x squared plus 2. There's an x squared plus 2 inside of cosine. So you know what? Let's just try this. By the way, sometimes you can try things and things might not necessarily work out. You can then try a different U substitution. But this is very effective most of the time. Take a derivative, you get du is equal to 4x cubed dx. And if I were to solve for dx, get dx alone, I'd get du all over 4x cubed. And I guess what we're really getting at is this. My dx, I know what that is now. So we could real quickly come back to this problem and say, well, I've got my x cubed right here. I've got the cosine, but in green, this thing I could really just call u. And my dx is really du all over a 4x cubed. And here's the real cool thing. I think you're going to quickly notice we're in business because x cubes are going to cancel out. Well, at this point, you can see you've got a 1/4. You can even pull that 1/4 outside of your integral. Look at that. And you get a much simpler integral right now. Such a much nicer problem to work out. Let's take the antiderivative of cosine. It will hopefully just take you a moment to know that that is sine. So I've got the sine of u plus a constant. But again, imagine that a friend is asking for help and you gave them this answer. They'd say, you're talking about a variable of u. I don't know what you're referring to. I don't know if we're looking at the same problem. You'd say, that's right. The u was just a help for us. When I'm writing u, I'm really saying that's truly x to the 4th plus 2. And once again, here's the real nice part. If you're worried about this, it only would take you a moment to take a derivative and make sure that you've truly found the antiderivative in question. So I hope this is going well. Hope this is making sense. I mean, if you would have seen these problems, at the 5.3 section, this would have been baffling. You would have just looked at that and said, oh my goodness, how in the world can I find an antiderivative? Take a look at number 3. Again, you're ultimately saying, is there a function inside of another? I see a square root, but I don't just see a square root of x. I'm actually seeing another function inside. So that's u is probably going to be 1 minus 4x squared. So, that's ultimately where we're going with this, right? So take some derivatives and let's see where we're going. I'll get du. And the derivative of negative 4x squared would be a negative 8x. Then we'd have dx. Solving for dx, getting dx alone, I'd get du all over negative 8. And the whole purpose for that is to make this other substitution. Now I know what my dx is. We're trying to change our integral drastically, so that it's going to actually be much simpler. Down below in green, that 1 minus 4x squared, I'm just going to call that a u. My dx right here, that's really du all over a negative 8 x. Pardon me, when I solved earlier, I should have said that dx was du all over negative 8x. Why is that so important? You need that. You want your x's to cancel out. You see, ultimately, you don't want to be left with an integral with two variables. You just want to see in this step an integral in terms of u. Well, this is really a negative 1/8. That 8 is in the denominator. And, 1 over the square root of u, I hope we'd all agree, the square root of u is u to the 1/2, but because it's down below, we could say that's truly u to the negative 1/2. Let's go ahead and take an antiderivative, though. As we do that, bump this up to the power of 1/2. Add a 1. Dividing by 1/2 is the same thing as multiplying by a 2. And we'll get negative 1/4. The 2 and the 8 are going to cancel. U to the 1/2 plus c. But remember what your u really is. Your u is 1 minus 4x squared. Now, could we write this as an actual square root? Indeed, we could. Another way we could have written this, it's very possible that Professor Stewart would write it like this in the textbook. This would also be right. But regardless of how you're writing it in exponential form or radical form, you could quickly take a derivative and confirm that you're right. Let's take a look. There are a few more problems. I guess there are 3 more, but let's take a look real fast at number 4. You're going to notice that these are bounds. We have a definite integral. This is dx. It tells us that our upper bound is x equals 4. It tells us that our lower bound is x equals 0. And that's very important, extremely important, especially in this problem as we're thinking about changing variables. I could quickly guess that a u substitution here, obviously checking first if we can, do this problem with algebra or just see an obvious antiderivative. We don't, so we'll try this u substitution. U equals 2x plus 1. We'll have du is equal to just a 2. When I take the derivative of 2x, I just get a 2, and then I get dx. And I'll see that dx is really du all over 2. So look, I'm going to change this integral. I'm going to change it up. I'm going to say, look, inside this radical, I've got radical u now. My dx, usually I've been having this little color scheme here. dx, another name for that is du over 2. All right, we can see that taking place. But our boundaries have to change. Our boundaries have to change. We have to change them with respect to u. So look, I want to be very emphatic here. This is a very critical step. It's a step that a lot of students miss when you have a definite integral. I think we get so focused on the substitution that we can lose sight of the bounds. If x equaled 4, well, you'd plug that in here. 2 times 4 is 8. 8 plus 1 is 9. You'd get u is equal to 9. What do we know? Our upper bound is actually a 9. Now, if x equaled 0, you come back here in blue. 2 times 0 is 0. 0 plus 1 is 1. So u would equal 1. So look what we're doing. We're actually writing a brand new integral where we won't have to go back and substitute back in terms of x. Certainly we could. That would make the problem a lot tougher. But look, right now, this is like going back to our fundamental theorem problems. I'm going to say this is 1/2, and I've got the integral. Look, I've got u to the 1/2 here. Maybe this will help us out a little bit. And let's just do our fundamental theorem. I've got a constant of 1/2 out in front. I'm going to bump my power up by 1. That's 3/2. But I have to divide by 3/2, which is the same thing as multiplying by the reciprocal. And then I'm going to go ahead and plug in my bounds. So I can see here my 2's cancel. So I'll have a 1/3 out in front. But when I plug in my 9 to the 3/2 I'll work out. And I'll have 1 to the 3/2. Hope 1 to the 3/2 is nice and simple. 9 to the 3 halves is really saying